Welcome back. Today we're going over 9.4, comparison of series. So we'll start with the direct comparison test. Theorem 912. Let 0 be less than a sub n is less than or equal to b sub n for all n. If sum from 0 to infinity b sub n converges, notice a was less than b, less than or equal to b. So if the big one converges, the smaller one must converge also. Similarly, if sum from 0 to infinity of a sub n diverges, if the little guy diverges, the one that's even bigger than that would also have to diverge. All right, so in this section, we're going to be asked to determine if the series will diverge or converge. So we'll start with n equals 1 to infinity, 1 over 5 to the n plus 11. So a similar series to this would be sum from 1 to infinity of 1 over 5 to the n. Now remember, this is something that we could rewrite as 1/5 to the n power, which would make this a geometric series with r less than 1. R is less than 1, this converges. So we found a similar series that will converge. Now we need to figure out how they compare to one another. So if a sub n is 1 over 5 to the n plus 11, and b sub n is 1 over 5 to the n, and we're letting n be at least 1, a sub n is going to be smaller than b sub n. The plus 11 in the denominator means we have a bigger denominator inside of a positive fraction. That's going to make a smaller result. So a sub n less than b sub n for all n at least 1. Therefore, we know that the series converges. So again, it doesn't say necessarily what value it converges to. We just have proven that, yes, this will converge to something by the direct comparison test. All right, so next up, sum from, again, 1 to infinity. This time it'll be 1 over 7 plus root n. So sometimes it might take a couple of cracks to find one that is similar but similar in a useful manner. So you might have noticed right away, okay, this can be made to look like 1 over root n, and we can turn that into a power as well. So So 1 over n to the half, which would make this guy a p series. And it's on the interval 0, 1, which means it diverges. But notice here we have the bigger one diverging. That doesn't really help us. If you need to kind of pause and look back at your notes, notice that we have cases where either the bigger of the two converges, meaning both converge, or the smaller of the two diverges, meaning both diverge. Here we don't fit into those categories, so we'll have to find something else. So since this doesn't really tell us anything about this series, we know that this one diverges. We don't know that the original does. We can try another one. We can try maybe some from 1 to infinity of 1 over n. This is also a p series. P equals 1, so we're still on the interval 0, 1. So this series also diverges. What's different and more useful about this one as far as the comparison test is concerned is that once n is at least 11, and you can kind of do just a table in your calculator of this and this. Once n is at least 11, if a sub n is 1 over n and b sub n is this 1 over 7 plus n to the half, we know that a sub n is less than or equal to b sub n for n at least 11. So now we have the little guy diverging, the big guy must also diverge. So this first part didn't prove it because this was bigger than the original and diverged. That doesn't help us. If the big guy diverges, it doesn't tell us anything about the little guy. All right, so then the next theorem that we get to play with in this is the limit comparison test. Let's get a fresh page for that. Theorem 913. A sub n is positive, b sub n is positive, and limit as n goes to infinity of a sub n over b sub n is equal to some L. L is a finite positive real number. So the ratio gives us a finite positive real number. Then sum of a sub n and sum of b sub n. Two things will happen. Either they both converge or both diverge. Yeah, you can look for some proofs of that. Kind of trim a little bit on the proof so we can make sure that we cover what we need to cover for the semester. But there are some proofs for those. All right, but for now we're going to not do necessarily every single proof in the book. All right, so we're going to look at sum from n equals 1 to infinity of 1 over cn plus d. C and d are both going to be greater than 0. So positive times n plus another positive. So something similar would be sum from 1 to infinity of 1 over n. This one, remember, diverges. B equals 1, which is on the interval 0, 1. So let's take the limit as n goes to infinity of 1 over Cn plus d over 1 over n. So that is then the limit as n goes to infinity of n over Cn plus d. Multiply top and bottom by 1 over n. So multiply by 1. We'll take the limit as n goes to infinity. That would be then 1 over c plus d over n. As n goes to infinity, d over n goes to 0, so this is 1 over c. Now remember, c was a positive number, so 1 over c is also positive. So we have a finite positive real number. So this is our L. So since that is both positive and finite, either both of these were going to converge or both would diverge. This one we know diverges, so this one will also diverge. All right, so next up, kind of a similar idea, sum from 1 to infinity this time, 1 over 5n squared minus 7n minus 11. And we'll use the comparison test with then 1 over n squared. So this is another p series. Here p is 2. P is greater than 1, so that one converges. So if this limit of the ratio of these two becomes some positive finite value, then this will converge as well. So we'll take the limit as n goes to infinity, 1 over 5n squared minus 7n minus 11 over 1 over n squared. So that's limit as n goes to infinity, n squared over 5n squared minus 7n minus 11. And we had both in top and bottom with, in this case, 1 over n squared. So we have the limit as n goes to infinity of 1 over 5 minus 7 over n minus 11 over n squared. As n goes to infinity, these two terms, of course, drop to 0, so this is 1/5, positive and finite. And since this one converges, both converge, so we know sum n equals 1 to infinity, 1 over 5n squared minus 7n minus 11 must also converge. Okay, so next one, sum from 1 to infinity. We'll do 4th root of n upstairs, n squared plus 5 downstairs. and use the limit comparison test to determine if this is something that will diverge or converge. All right, so that one I'm just going to ask you to pause it, try it out, and then play it when you're done. Okay, welcome back. So here, again, I tried to set up something similar. So n to the 1/4 over n squared. So I just kind of use the leading term, top and bottom, which is sum n equals 1 to infinity of 1 over, so this is, let's see, 1/4 over 8/4. So it's 7/4. So here p is 7/4, which is greater than 1. So what we're comparing it to converges. Now let's see if we can actually reach a limit, though. That is both positive and finite when we approach infinity. So limit n goes to infinity, n to the 1/4 over n squared plus 5 over 1 over n to the 7/4 power. So that's n to the 1/4 over n squared plus 5 times n to the 7/4 over 1. And of course, we're still approaching infinity. So then the limit as n goes to infinity of n to the 8/4 is n squared over n squared plus 5. Hit the top and bottom with 1 over n squared. So n is going to infinity of 1 over 1 plus 0, which is 1. That is both positive and finite. So they both diverge or both converge. The one we picked for comparison converges, so this converges. Okay, so one more of these. Sum from 1 to infinity of n times 5 to the n over 8n to the 4th plus 3. So again, I want my comparison to look similar. So what I'll compare it to, I'll still add from 1 to infinity. We'll keep the top the same, n times 5 to the n. Downstairs we'll simplify a little bit, 8n to the 4th. Or let's leave the 8 off of it, just n to the 4th. So we'll simplify that down to sum from 1 to infinity of 5 to the n over n cubed. As n goes to infinity, 5 to the n over n cubed. Right now we have infinity over infinity. We can use our friend L'Hopital. So that's natural log of 5 times 5 to the n over derivative of n cubed is 3n squared. Still infinity over infinity in form. L'Hopital again. So we still want the limit as n goes to infinity. Natural log of 5 squared times 5 to the n over 6n. Still infinity over infinity. But one more crack at it with L'Hopital, and then we have limit n goes to infinity of natural log of 5 cubed times 5 to the n over 6. infinity over a constant goes to infinity. So this diverges. So if the comparison leads us to a nice, neat, pretty positive finite number, then both will diverge. So we'll do the limit as n goes to infinity. So our original guy was n times 5 to the n over 8n to the 4th plus 3. And then our comparison, we had n, we'll do the cleaned up version, 5 to the n over n cubed. So that is then the limit as n goes to infinity, n 5 to the n over 8n to the 4th plus 3 times n cubed over 5 to the n. Goodbye to our 5 to the n's. So limit n goes to infinity, n by n cubed n to the 4th over 8n to the 4th plus 3. So our limit there is 1/8. So think of multiplying top and bottom by 1 over n to the 4th. We get 1 over 8 plus 0, 1/8. So that is both positive and finite. And since the one we were comparing to diverges, both diverge. All right, so from 9-4, I would recommend 3 to 27 odd, 29 to 36 all, 45 and 47. If you have questions, get in touch with me. Otherwise, stay safe out there.